nicely lined up text and arrows coming into what you're doing. So in that box you'll notice I have my special box of grey things, which I gave you a nice little tick for the things that you hadn't done right. Some of you on assignment one took one look at it on about a Thursday or Friday night and went, nah, can't be bothered doing that, I'll carry on doing that for assignment 2. Surely you won't do it again. Yep, we did it again. Some of those people aren't here. And it's the same with that. It's just, if you keep doing things that Ingrid would have been upset about, then obviously at this higher level I'm not going to be too happy about it either. It's a bit like passing communications, going into project, which is the very last subject, and then starting doing spelling mistakes all over the place and grammar errors and stuff like that. I mean, obviously Hugh's not going to be over the moon about that. Yeah. So that's where we're at. We've got 3 weeks of I'm sure I put that on, but obviously it required another push of it. And that, yep, another way. We've got a electrode concrete, which is probably the most intense one. I'm getting a bit nervous about my friend coming in here as I'm still waffling on and putting stuff on the board, and as you know, she's just took for time. So we might cover a bit more of it in the lab before we start the lab off. The lab's really important, and if you want to film it, good on you. It's a good idea, both of you guys. The lab is going to be, I'm going to go over an example. What you're going to have to show is some reinforcing in the slab that looks a bit like that. And every year I change it a bit. Sometimes I have the reinforcing coming down and round and up, and down and round and up. Other times I have it so this stops there and that stops there, and then we have another bar that goes and overlaps there and there. Right? So every year it's a wee bit different, but the principles behind working it out don't change. So this is basically what you're doing. You're going to have a slab of concrete, you're going to be a bit of an overlap. This year, or this semester, they're going to overlap down the bottom there, like that. And going that way into the blackboard, because obviously a slab is not just a very thin piece of concrete, it's off like that, isn't it? So these numbers going this way repeat themselves, and you've got to work out how many there are, and there's a calculation for it. Some people take to this like a fish out of water, other people just sit there staring at it for hours, not knowing what the hell's going on. It's one of those things that you've got to sort of think in 3D. So if we take that out of the perspective, we're going to be doing a slab, and there's going to be reinforcing running in that direction as well. Alright? Now when we're talking about reinforcing, we're talking about spaces and working out how much there is between them. Now, to be honest, if you made small errors and it went out to site, the steel people that do this, you've probably seen them on site, they're tying all the steel together, they're keeping it off the hole so that the concrete can be poured all around it. Those guys are pretty experienced. So if you made a mistake by 10 mil or something, it probably wouldn't matter too much in terms of getting this perfect. I'm just being honest about it. With me, it does matter. You lose half a mark or whatever it is, right, because you didn't do the calc right. But on site, they will just adjust it. And your first job probably will be in your engineering, if you're a site slash design engineer, so you're out and you're inside, which is the perfect job. outside sometimes in the sun and inside in days like this. Your first job will be probably to water the boss's pot plant, because it always needs watering. The second job will be you're going to go on site, right? You get on site, and if I was in charge of you, I would say count the bars. The first thing I do, text probably, count the bars. So you go 1, 2, and if there's not enough, you have to tell this guy that's about this wide and this sort of big. You're always big fellas. And I'm being sexist here because it's not really a woman's job to bend the reinforcing bar, but we do have things that make it a bit easier. They don't all just go like that and put it in, but you know, these guys, well, I could tell stories till the cows come home. I worked on the Clyde Dam. We've got a guy, a Steely, who was from Marsden Point. In those days, the gangs got involved with the unions, and if you didn't put your hand up to say you're going on strike, you would get a strike on the back of the head, because they'd set the gangs up along the back, it's a 4x2 literally, for anyone that complained against the union. So that's what it was like there. If someone fell off the 6th story and landed on a piece of reinforcing that went right through them, they basically had to go over there and console them until, not the ambulance arrived, but until that was the end. And he's telling us the story of this guy with reinforcing on a spike, and I'm trying to eat my lunch. You know, that's the sort of guys you're talking to. So you go to a guy like that and you say, hey mate, you got it wrong. You got one reinforcing bar. I said, you want to see the smoke coming out of his mouth, right? You know. If he's a private dude and he's working privately, that's money. And if he's in Indonesia or a third world country, that's big money. That's a week's wages, one bar. So he can sneakily take one out here, one out there. You know, I mean, who cares if the building falls down in 10 years' time? He's not around. Technically, he's saved big dollars, and they'll just go on to the next job. You know, and once the concrete's poured, who's going to prove it? So, as a young engineer, it's probably the most important thing you're going to do is go and something like those bars. And the other thing is to make sure they're evenly spaced. A lot of people think you do the calculation and the bars are every 300 mils. You start at that end, you get to that end, and you end up 2 bars right beside each other, and you think that's proper reinforcing. Well, that's not how it works. The calculation that you've done means it's evenly spaced at 300. So you have to bring it back to 293 or something like that to make it work all the way across. So the one we're going to do is going to look a bit like, I think that, off the top of my head, or is it that? If it's not that, it's definitely that anyway. So it's a reinforcer, it's a retaining wall, that's a slab. But the calculations to work out how many bars that way are exactly the same for those dots as working out how many dots that way. And working out how many of these funny looking ones here, if this goes like that, how many of those go that way is the same calculation as working out how many go that way in the slab as well. All right? And working out vertically how many there are is the same way normally of working out how many vertically there are that way. However, the slab you're often told how many there are, whereas this one is a calculation that I will need to show. And that will be in the test, that particular calculation, so it's important that you get your head around it. Nothing's hard, it's just remembering which one it is from to work out. So sometimes they take the distance and they take the cover away and divide it. Sometimes you do it centre to centre of the bar. And that's kind of, and both the test, not exam, the test has it right to a point where if you do the wrong calculation, you get the wrong numbers. Because sometimes you can get the same number, and also the assignment's the same. All right. So that's the concrete. The steel is relatively straightforward. We'll be using some columns, and a column is a fatter version of a beam. So a column sort of looks like that more, and a beam kind of looks more like a very skinny and tall. It's sort of a bit more like that. So beam's more like that, it's thinner and it's normally skinnier, whereas a column is normally fatter and normally a similar size both ways. You can use a column as a beam, but if you're involved in the calculations, it won't go as far, and it won't span as far, and it may have to be quite a bit deeper as well to work. So that's why we tend to use a thinner beam. I'm only doing a bit of a sketch of one here. You'll see them in my notes. We tend to use those as beams and those as columns, which means we turn them around. Well, there's a column over there. That's if that was a steel, that would be a column going upwards. I've already told you that there's more reinforcing in there than anywhere else in any building in the country, so you'll never find a column that size in a 3-story building in New Zealand. They've really gone over the top because this was built as a civil defence building. Whether they still use it, I don't know, but we're pretty safe. Plus, Auckland doesn't really have. I think we had our first earthquake in 2013. We got a 4, and my coffee on the table, we were like that. And that was the worst one we'd had for something like about, 20, 30 years. So you're in a fairly safe place here. Mind you, Christchurch they're safe too, but... Yeah. Actually, the building that killed the most in Christchurch was actually designed to fail, and it did fail the first time. And most of the beams were sitting like that, right on the edge. So they had so little amount of people down there that were able to go around and check everything between the first earthquake and the second one, and no one was able to pick that up. So they were just basically going around looking at cracks in the building and going, okay, everybody needs to go back into your building now. So that the actual design actually worked. It was just that they needed to make repairs, and then of course the second one, very easily pulled off their console all the way down. But anyway, that's the more topic for a first day back. So some of you would have seen your results, some of you may not have seen your results. I've got an unusually high strike rate this time round, which is good. Doesn't mean I'm going to try and get rid of you all because of it. It's pretty simple to follow your marks on my subject. Some of the others, they have like 5%, 10%, and everything's out of a percentage. So you get a mark like 93% in something, and you get another mark of 59, and you think, I'm doing well, but the 59 could be in the one that has the most weighting, and it gets very confusing. Mine are straightforward. That's why I try to keep my marks. Each mark is a progress towards getting that magical 50, or if you're going for a B, the magical 65, okay, or A is 80. So if you've got 55, you've only got to get 45 in the second part to pass the course. You don't have to pass the second part as well, just putting it out there, okay? Not saying that I don't want you to, but that's your target. If I was purely honest about it, if you can get within one, you've got a pretty good chance of the examiners meeting bumping you up. Get within 2, we start going back to things like, have you been attending class? What's the student doing in other subjects? Have they been a pain in terms of this, that, and the next thing? And we talk about you in terms of how long you've been at Unitec and blah 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 blah. So there are different things we talk about which you keep behind closed doors. For example, it could be your last subject. This could be the one that gives you your diploma and you're only 2 months off. So there'll be a lot of people pushing to pass you. Whereas if it's just your 3rd or 4th subject, 48 isn't a pass in my book, but it's other people think differently. If I get told to go back and find marks, then I will go back and find marks. The quickest way for me to find marks is to take those negative ones off, and then you pass the course. But of course I can't tell you that I've given you 2 more marks, whereas he's going to want 2 more, even though he's sitting on an A++, he wants 2 more marks. Of course he does, isn't it? So that's all kept in the examiners meeting. And that's kind of how it works every semester. So when you see my assignment today, have a look at how the mark distribution is and see what you will be strong with and what you may be weak at. I suggest you immediately start concentrating on the stuff you think you can bang out, because it's worth 40 marks, and I've broken it down to 2 marks and 3 marks and 5 marks. So yeah, that's what I would do anyway, just as a tip there. It's not due till June, I think. June, yeah, but that's going to creep up real quick, especially with exams coming up. So the more you can do when there's not stuff on other subjects, the better. Alright, so, and unfortunately, because we're going on to millimetre drawings, some of the stuff changes again. So the text heights, you'll have to do a different calculation. It's actually not too bad, it's just the text height times the scale gives you the millimetres to draw them on. So you don't have to divide it by 1,000. And I think at the end, of course, we have a little 10% quiz test, whatever. Most of that is on the notes, but it'll be pretty much the same as last time. It'll be a half theory, or multi-choice, and half of it will be doing things like calculating, reinforcing, and the other structural things that I teach you. There's talk on the degree, it probably doesn't bother a lot of you, but some of you may switch over to the degree at some point. Let's talk about a level 7 course now for drawing, so we'll see where that goes. At the moment there's a level 6, which if you get 60% on this, you can transfer over to the level 6 course, and it can be an elective for the diploma. But the level 7 is looking at quite advanced stuff to try and compensate for the companies to have to teach you that part of Revit. So it'll be more structured, it'll be sort of, but watch your space. Should be quite an interesting course. And we'll be the first in the world to start developing that at an institute, because that's the sort of stuff that normally companies teach you when you get into a company, so it'll make life very interesting. I'm not quite sure what's going on here, so I have to sign into Google.
Got it, and then it goes.
So just where you've got it.
Yeah.
So, always go back and have a quick look at the timetable every now and then just to make sure you're on board. I have had students in the past going, I didn't know we had a test this week. I thought Handon was next week. It's been there since the beginning. There it is, 9th of June. Alright? Now that date won't come forward. We're not allowed to do that to you, but it may adjust in terms of there may be an extension of some sort put on that. The issue, unfortunately, with the last one is that I have to get all of yours marked and into my moderator and into the exam system. So it gets harder the longer I'm waiting on someone to hand in. So let's make a few things visible. So those with the computer at the moment, assignment 3, and I said I'd bring this up. So with assignment 3, we've got a building, obviously that's the Concentrics storage building. So if you do know any students who were studying in 2014 semester 1, you've got a great chance of passing this course.
How do we find that? Do you have email?
Otherwise, this is, it has been changed slightly. It had 2 of these beams across the front and the back. So there we are. It's not the most complicated of drawings. Last semester they had to draw up a truss, which was rather difficult. This is to help you kind of see how everything fits together. So it's a concrete base. There'll be some Dynamolts go into here, into each one of these plates. There are 10 or 12 mil plates, I can't remember which one. There's one at the top. Now the plates are welded, so we cover welding, we cover bolting in the notes. They're bolted again to the top here. These purple members are what we call purlins, which is where your roofing line normally fits on top of. And this is an angle. Angles are like a letter L, but obviously there's the L and it's extended, and there'll be a couple of screws going into the timber, and there'll be a couple of bolts going down into the metal. We'll get to screws, bolts, metal, steel and all that sort of thing in the next couple of weeks. As a general rule, if we're going into timber with a bolt, we tend to use washers. Otherwise, the nuts just end up going into the wood to a point where they disappear. Alright, so we tend to put a washer in and then the nut, and then pushes hard against the timber. We don't always use washers when we're bolting into steel, because the nut ain't going to go anywhere once it's a solid steel. There are different reasons why we do put bolts, but generally speaking, If you use that rule, you'll do okay. You're going to do that 3D sketch for me as part of the assignment, and don't worry, I'm not going to draw anything else up. I'm just going to start. I'm going to do a little bit of an Ingrid here. I will draw that up, so you can record it if you want to. But you're going to have to take over the bit where you put it into a viewport, and you maybe rotate it round. I want to see a good view of it. Now that's a good view because you can see what's going on. A lot of students just put it in the viewport and they have just a front-on view or something like that, or an upside-down view. I've seen a few of those as well. So, you know, it's up to you to get it and zoom it to, I don't want it the same size as the postage stamp. It needs to be out, you know, to a reasonable. Now that's not fully out, but it's you know, pretty good, right? So some of it, as I said, for 3 marks out of 5, I'll draw that up. Then I'll leave you to it to start seeing if you can get a few more marks. You can get nuts, bolts, screws, all that sort of thing off the internet. Word of warning, you're going to need about 4 for each one of those plates. You're going to need other ones around the place. You'll be getting up pretty close to 100, 150. So you pull them off the internet, and if you want to see your laptop at home start going slow, or how to break the ones at Unitech, that's the ideal way to do it. You can draw your own nut and bolt up very simply with a cylinder, a circle that's been extruded down, or drawing a nut head and extrude that. When I say extrude it, give it a bit of thickness. You'll see what the extrude command is when we get to that part of the assignment. You're given a example template of for the assignment 1 of what's basically required. You'll need to add some notes to that, but you'll have generally the concrete. So I'm going to make you do a calculation on the concrete. Just pretend there's no reinforcing there, so the actual 3D, I suppose, of the concrete. To most of you, that should be an absolute piece of cake. It's amazing how many don't calculate it right though. Also, when you see in the sketch, there's a trench on either side for drainage, which goes right round. That gets a bit complicated. There's going to be a pipe in the trench. So you're doing the quantities involved in the job up the top there. Timber is very simple. It's 1 purlin, and the length will be pretty obvious when you see the sketch. So if you don't get 100% in that, you've got a problem there. You can't just put purlin. You've got to put the nominal size of the timber. We will cover that in our notes. So remember nominal size. But that size can reduce if the timber is gauged or dressed. Dressed isn't like putting your clothes on in the morning. Dressed is when you really make that timber look nice, ready for painting. So you've got 3 types. You've got rough sawn, which is your first blade through the timber. It's often burred. You know, it's a bit. You get the best value at a rough sawn. It's sometimes a bit bigger than 150 by 50, so it's stronger, bigger. A lot of people use it on decks. Underneath decks, we don't see anything. You know, places where you're not going to be painting, because it's a nightmare painting rough sawn, believe me. Gauged is probably the best one outside for painting. You're still getting fairly near the same size you want. And dressed takes it down about from a 150 down to about a 140 by, if it was a 50 it might go down to 45 or 40. So you're losing quite a bit. So as an engineer, if you've ever calculated a beam, you get constraints to calculate it to. And sometimes you fall out of that by making your timber dressed. So there's an architectural versus engineer thing already. Architect says, I want the timber dressed, so it looks pretty. Everyone's going to be happy and say what a great job I've done. The engineer's saying you can't do that because you're dropping the timber size down to a point where the building's going to fall down. So you have that conflict starting straight away just with timber members. Steel, yeah, we will have our class next week's lab will go over a steel schedule. Scheduling steel is not as easy as it looks. Once you get the hang of it, you'll be fine. You'll nail that's probably the wrong word. You'll easily do the columns, the beams, and the plates, and you'll struggle with the little angles because they're going to make things a little bit more difficult for you. So, like in a lot of classes in engineering, it's easy to get a quarter marks. It's reasonably okay to get half marks, and then it gets harder to get more after that. The reinforcing schedule, the bars running in this direction are going to be easy to calculate. They're straight bars, okay? So if you nail that, you're pretty much going to know how many there are. That may be a tricky one. These ones will be the harder ones to calculate. And I'll tell the past student they're not allowed to give you too much help with those two. So that's what you're going to produce for me on in terms of a schedule and a reinforcing schedule. That's schedule quantities, that's reinforcing. That's an example, so you'll have to draw that up from scratch. Back to here, the sketch of the building, two angles. I don't know how do we rotate that? Oh, at the top of this road. A little bit hard to see, but when you zoom in, you can see these things. There's my squiggly lines. So you can see the beams being called up there, and the reinforcing bars being called up. It's the ones on the bottom. The dots are at 300 spaces, and the ones on the top are at 200 spaces. Now, when we bar schedule, we have a number here. See that 1203. The 03 is just a sequential number. So, okay, I'm going to do a bar now. Let's call it 01. Okay, here's another bar. Let's call that one number 02. The 12 is, and the 16 along here a bit further, that's the diameter of the bar, and we'll cover that later on in the notes as well. The diameter, the centres is given there as well, but there is a way how we call those bars up properly, and we'll show you that in an example. Now just note that under here is some hard fill, which will require some calculations for how much there is. And down here we have a very important table. Now there are ways to calculate these things in my notes if I don't give a table. But if there is a table given, you're supposed to use the table. So don't come back to me and say, well, I calculated the bend allowance to be 27.95. And your table's got it at 27. So I used my calcs. You'll get it wrong. Use the table, you'll get it right. So we'll talk about a lot of that in today's lab. Minimum lap, bar diameters versus the bend allowance. The bend allowance is when you're calculating the overall length of a bar. This was my bar here. Unfortunately, even the strongest man in the world can't bend that at right angles. There's got to be a curve in there, and they actually have the bigger the bar, they have machines. They put it on the machine at the exact mark, and the machine will just bend it, so you don't need a strong man, but there is a minimum curve. And of course what that's done is that's reduced the size of the bar. It doesn't feel like it has, but it actually has, because you've cut the corner by doing a curve. So in that particular case, a 12mm bar, you lose 27 mils on both sides or on any corners, no matter which way it is, that way or that way, you lose 27 mils. The other direction is the other sketch. So, someone said rotation was over here, was it?
To the left. So, in the middle.
Yep, okay, thanks. So that gives you your distance of your slab going the other way. Now, because that's through the middle, lengthwise, you're not going to see it's this way through here. So you're only seeing that bit. Yes, that bit's in the distance, but I've got it cutting through the hard fill. So I could have dashed that, and if you're going to draw it, perhaps you should think about dashing it. But at the moment, that's the sketch that I've given, so that's what you're drawing it off. There's some notes up the top there. There's one or two that I should point out. Now, you may use these. Unfortunately, I do get students who go copy paste. Wow, I've just got 4 notes, and I've got to find 3 more. And one of the notes says, calculate using a table from your concrete notes on Moodle in week 8. You know, that's not what you put on a drawing. All right. Now, sometimes my notes might say students to calculate blah blah blah. You don't put that on either. An easy one is the cover. That should go on all drawings. If you're also looking for one, you can put your 28-day MPA, which was something that the materials was covered in materials. If you want to look back on materials notes, but there are many other things you can put on this because it's going to have concrete, steel, and timber. For example, the timber is probably best to be tannalised, which means that it can be left outside. So you're probably going to have a rating on that. We'll cover that in the notes as well. I know I'm a little bit all over the place, but I like to give a general idea of assignments before, so students know what they're getting into. And I'll let. So the assignment talks about the things that are given to you. Like you're also given 3 steel members. I want you to use those on AutoCAD. So there is a beam, a column, and an angle like this. So I want you to use the ones that I've given you. Start drawing that up. I'm suggesting the order I've done is the suggested order. You don't have to do that. Start with the last thing if you want to. Start with. There will be a 3D demo in week 4 of structures, so in 3 weeks' time I'll be doing that 3D demo. Seriously thinking of that going online because it may help people to bring it up, the video at the same time. We'll see what happens. If I don't do it online, I'll be doing it in the lab down there, and you'll need to film it, or somebody will need to do that, or take notes. There's the distribution of the marks. So you saw already there a reinforcing schedule for the bars, 7 marks. Oh, and a drawing of a foundation slab So, what I'm requiring is for you to do a plan of this, looking down on it. Okay? And I don't want to see every single bar, I just want to see it pulled up the normal Kiwi way, Kiwi standards that I'll teach you. If I go back to, where are we now? Simon. If I go to week 8, somewhere here. Week 2, week 3, week 4, week 5, week 7, week 8. Example. So here's an example of quantities. So you'll note with the quantities that it's not just all about working out the length of a piece of timber or how many there are. It also can be, you're going to have to put the RN number and the tantalised number there as well. And the bolts are the same. It's not just all about the heavy duty stainless steel bolts. You can't just call them bolts or Dynabolts. You've got to pull up a description of them as well. And over here with the reinforcing steel, it can get rather complicated. And up the top, well, you can see that this is an example from the past where you have a straight line along here and you have a piece at the end that ties them together, this piece here. So although that's not what you're doing, it gives you a good example of how that one was scheduled. And plan. Right. Alright, so the reinforcing plan, as you can see, the dashed line shows, looking down, shows there, the footing on the other side. And you can see the laps in the middle. And you can see that anything joined to there, see that circle? That's telling you that there's a circle there. That's telling you that that bar goes from up the top there, just a wee bit of a gap for the cover, and all the way down to over here. Now this gets a bit like that game on your cell phone. I don't know if any of you young ones play it, but where Tetris it's called, where you bring a shape down and you bring it in and another one's coming down and you've got to put it there. I don't know if you've seen that before. It's quite a tricky game. I've seen people playing at airports or whatever, killing time. You aren't allowed anything to go through any text. So you can't have lines going through any of the call-ups for the bars. So the call-up basically is a number, 34, D, or whether the bar's deformed or not, 12, the diameter of the bar, 04 is a mark, so that will be 01, 02, 03, 04, depending on what number it is on the bar schedule. And there's the spacing, in this case 250, that one's 200. And where it sits, is it at the bottom? So is it along here? Or is it the top? Alright. However, on this one, the bottom is all of this, and the top's the top section. So it does vary a little bit. As I said before, I worked on the Clyde Dam, and it was very different for us. As if we were out by 10 mil, when they brought the cages of reinforcing down, they came down by crane, and they were out by 10 mil, it would just go, it wouldn't fit, wouldn't go like that, it just, of course the steely's up the top, the head steely's down the bottom, because he knows if the Germans, who we work for, were going to pretty much execute him for getting it wrong, and he knew the drawing office was the ones that got it wrong. So he would have to send the crane away, and would come back up. He'd then go to the drawing office and find out the dimension and work out what we'd done wrong, and come back and chop this up or replace the bar. Meanwhile, the crane's sitting there. Right? There was 2 cranes going 24/7, 3 shifts a day, pouring concrete. Each time the pour went over is 10 cubic metres of concrete. And Germans being Germans, just like their trains and everything else in their life, they calculated down to what second they were going to finish that job. So when the reinforcing came down and then had to go back again and the crane was waiting, that was one pour, another pour, another pour. So it ended up in a big fight. They would then put in a VOE to the Ministry of Works in New Zealand saying they wanted X amount more money for doing the dam because it was obviously going to take them more time. And if you don't think that's ruthless, how about the very first day on site? You know how the first day on site, we're talking about a closing in those days, closing on $1 billion job. First day on site, the Germans dropped the drums exactly where the Ministry of Works wanted the site huts, put onto drums, ready to put the, some timber underneath. This is site huts where the engineers, hanging out all day. And the Ministry of Works chief came out and said, it'd be a bit better if you just moved it about a foot that way, and we can all see the dam a bit better. And the Germans went, no problem. They all moved it another foot. And the next day, the first DEO went in VO number 1, moving site hut, and there was a cost for doing it. I mean, how to get up someone's nose really quickly. They actually employed a couple of Kiwi guys every day to work out the costs extra they could charge on the job that wasn't part of the original contract. So, one of them was a hard case. He had a saying. The rock that was there was called schist rock. Now, hopefully most of you don't speak English. Don't speak German, because schist means something else in German, okay? And the Germans used to say, the New Zealand schist makes us more money. No, which is ironic, but it was. It started off looking like that, and by the time they carved away all the schist on the side, the bottom would look like a cruise boat rather than a yacht. So we had to be particularly careful to get the reinforcing right, or else it started with this Dealey guy. He just went berserk, and you could just about set your clock to the Germans. They would come down the corridor, and that sounded a bit like a goose-step march on the floors of the huts. They would not only get the privilege of blowing us up, but then they would charge the New Zealand government extra money for blowing us up and getting it changed. You don't want to be operating under that pressure. There was also times where we were told to go down the hole, measure up, design it, and bring it up and draw it up, and they put the reinforcing in that day. So I'm giving you a month and a half to do this. Sometimes we were given a day. And if that wasn't bad enough, most of the Kiwi workers didn't like the German workers. So if they saw a white hat down a hole 100 metres down, they would throw something down there at it. Or actually they'd kick a stone, which would go down towards the white hat And the Germans used to say to us in the drafting office, "You are going down the hole, and today you will be wearing the white hat." So that was the kind of punishment for getting it wrong. The amount of dents at the top of those white hats. Anyway, I digress. By the way, the job went something like 3 years over. So, yeah. To the notes. We'll whiz through the notes. So today in class, in the lab, we're going to go through an example of how to schedule something that looks like that. And you're going to have to try and relate that to your slab. I've also drawn up a water course channel. Looks like that. That has some reinforcing in it. And I've drawn it up with the dots and what have you. We call them actually donuts. I hope Ingrid showed you how to draw a donut up when you were doing your reinforcing. I'm pretty sure she did, because I've been telling you that if you show them that, they'll know how to draw it up for mine. But I've got an example CAD drawing you can have a look at. You can use bits of it if you want to, or just work out how it works. So all the calculations for this one I can make available, and the one I'm showing you have to do your own notes off the blackboard. I've got some condensed ones, just with kind of the answers, but you can, do your own notes on how to get to it. The trouble with Revit is that you can hit a button and it will do all the reinforcing drawings for you, but they're not necessarily right. You still need a certified engineer to do the proper calculations, and then if it's not right, you then need to redraw it. Okay, and sometimes it's a simple redraw, sometimes it's not, but you guys would have, part of your job would be to say, well, here's the Revit drawings, are they right? Because the computer isn't always right. That's the problem. It's the same with beams and all that sort of thing. So we have the notes, should have been made available. If they're not, we'll go to week 8. I'll make them available now. I'll let you guys read through these more intensely on your own, but what I'll do here today is to just point out the sections where my multi-choice questions come from. If you've got your laptop open, you might like to put a mark beside where I'm talking. If you've got a notes, if you're recording, it's fine, you can go back and do it. If you've got notes, then you might like to type things like specify concrete, types of concrete, or plain concrete, something like that. And that will remind you to go back and read over those. What is helpful, of course, if it turns out to be that it's a open book online test, then and you've got notes there with little highlighted bits, and there's a question on, say, plain concrete, you should be able to go to that really quickly to answer the question. So having said that about concrete, we go into detail here at the beginning about the differences between reinforced concrete and plain concrete. A lot of it is obvious. You would use plain concrete on things like driveways and what have you, whereas reinforced concrete, you'd use it on buildings and things you need to reinforce properly. There is a question on plain concrete versus reinforcing concrete. And also a question on the scales that are on a reinforcing bar. Why do we do that? And the answer is to stop the shear forces. So the concrete goes around the reinforcing bar, but when you've got those ribs on there, it stops the bar doing that sideways, the shear forces. This you would have found already under structures if you've done structures, or you would have found it already even in the early stages of fundamentals. They talk about things under compression and things under stress. And obviously concrete resists compression, but it cracks under stress, and that's why we use reinforcing. Do you still do that testing concrete thing down in the labs where you crank it up until it cracks?
I don't know yet. We did do that. Don't know yet, but maybe.
You will do that
In the next like 2 weeks, I think.
a couple of weeks' time with the concrete you made? Yeah. Yeah, I did mine in Upper Hutt, Wellington. I'd come all the way up from the South Island. That was in my time. You had to do your labs in Wellington. And the stupid teacher walked out of the class, and we had a real nincompoop in our class who was one of the students. And he replaced the concrete with a bit of steel. And he cranked it up and cranked it up and cranked it up, and he said, "Oh, nothing's happening." And he cranked it up even more, and suddenly there was a loud bang like a gun, and this piece of steel, I kid you not, went right across the room and into the wall. Missed at least 6 students standing over there. I know. It was a wake-up call. So, yeah, just don't do that. Try not to, okay? That's a very good example of what reinforcing looks like when you go on site. This one here on the right-hand side. It's called caged reinforcing. There's normally the larger pieces of reinforcing are held in place by smaller, what we call tie rods or things like that. Sometimes it's wire, sometimes it's smaller reinforcing bars. They did that. I don't know if any of you have driven on when you come out of the tunnel and you go up and over in those big large. Yeah, well, one thing that fascinates me is someone's done design and it's all held up by one pole, which seems a little under-designed, but anyway, it's nice when you've travelled on it and got off it. This is a picture of the guys doing it way back when they did those piles. So they had their reinforcing down here, which looks a wee bit like a king's crown, and they put the cage in, and then they the crane lifted another king's crown on top, and it went up, and then they do another cage and so on. So they did it in pause, and before they did each pause, there would be some concrete sticking up to tie, some reinforcing sticking up to tie the next one onto. And you often see that on site. There's a little bucket on top, a little wee knob on top of it, a little plastic thing. That plastic thing, by the way, wasn't around back in the days of Marsden Point. That's why guys would fall off buildings and go straight through. So, yeah, they decided in their wisdom that that they would bend them, and that would take care of that problem. But they had other problems from bending the rods, so they went for the plastic. I still think coming off a 6-story building, you probably, yeah, it wouldn't be too good for you. But anyway, that's for people that trip on the slab. Yeah. I know. Talk about falling on the sword. So that's what the Clyde Dam was. It was what we call a gravity dam, which means that the only reinforcing in it was around these things called galleys, which were the most scariest things to walk through. They always had dripping water. And they usually had a chute looking straight down it, which is where the surveyors set up their survey equipment to see if the dam was moving. So don't even millimetres, they would be tracking that. Once again, the surveyors had white hats on. Once again, some of the workers on the dam thought they were Germans, so they would do stupid things like throw rocks, or in one case they threw a glass Coke bottle. They let one drop down the chute. The poor surveyor was just in the process of doing the. Yeah, it was a pretty. He came into the office and he had his hand all bandaged, and I said, "What happened to you?" And he said, "What happened?" So it was pretty hard to prove anything back in those days. There was no cameras on site. So when they did the reinforcing, we did it in stages, and we always had bars sticking up out of the concrete. And if those bars weren't accurately placed, then the next cage wouldn't fit down either. So they had to be perfectly in place as well. So you can sort of see the enormity of the job, plus the importance of getting things. 10 mils was no good because a rod might have been 15 mil. It just wouldn't fit in the gap if you didn't get the gap right. So the gravity dam, basically the gravity of the concrete is holding back the water from basically taking out all the small towns further on down. In situ concrete, there is a question on that. There's also a question on precast concrete, but before we get there, concrete is also used for things like, here is also gravity, but it's a gravity retaining wall, and because it's set back each time on an angle, it's able to retain all that dirt and garden in behind it. Also a common thing to see all over the place. Don't know what lake that is. Precast. Precast concrete is where they put the reinforcing in it and they stretch the reinforcing, so it's all pre-stressed. They pour the concrete and then they take the stress off it, and it's basically precast, pre-stressed beams. Used a lot on things like motorways, as you'll see a road going across the motorway. They can do them really, when they're all pre-stressed, they can do it really quickly, so they can do it overnight. They'll do a rolling stop and then they'll make the traffic go around that part of the motorway, and these things will go on the back of maybe 2 trucks, and they'll carefully get a crane, they'll put them in position, and they'll actually have them locked in position and gone by the rush hour the next morning, which is pretty impressive. And so they do have that advantage of being able to be compared with concrete poured, manoeuvred on site. There's a lot of advantages in pre-stress. However, the concrete you'll be, here's some examples of twin T's and uni T's. Mount Albert, Pack and Safe's got twin T's. We designed that when I was in industry because of the roof height. There's a lava flow comes down through there, and they dug out for the car park, and then they realised that they still hadn't dug enough for the roof height. It's actually a very low roof when you go under there. So the Uni-Ts had a large drop down, whereas by going to 2, you could get more height under there for parking. So they got around what would have been a lot more excavation, because with the rock you've got to basically either dynamite it or it's really big. You've heard them up here, haven't you? Just all day drilling it and breaking it. So, yeah, that's how they got around that at Mount Albert. There was the disadvantage on that, and they didn't know it was going to happen, was with the twin T's, they're more bouncier. And at that stage, the Pack and Save wasn't full of any, because they're all designed to take the weight of all the product that's up there. There was no product in there. And the forklift driver was, it looked like he was on a trampoline. He was going along like that, up the top. Yeah, it's quite comical. Once they got some weight on it, it started becoming okay. But whereas the single T, for some reason, didn't have that same bounce about it. There's an example of slip form concrete, which basically means they pour it, then they move it up a level and up a level. They do a lot of car parks that way. It's quite a quick way of, it's all pre-stressed, comes in pre-stressed, poured and pre-stressed, and then they stack it and pull it up. That's why you might go somewhere like Newmarket, and you go back the next day and there's a car park where, there's just bare land. It's quite a quick way of building. It's also a quick way of building out by the airport if they quickly want to build somewhere to store stuff. The concrete that we're mostly going to be talking about this here is going to be in situ, which is Latin for on site. So it'll be concrete that is poured on site. So you'll dig a hole, you'll put what's called formwork in there, which will be either large pieces of steel which they wash down and move along to the next section, or it'll be timber which gets thrown away, untannised timber. Sometimes you reuse it once, maybe twice, not as much as steel. And what a lot of people, this is a question in the test too, the difference between formwork and false work. Formwork is this. That's where the concrete is, right? So formwork's holding the concrete back and keeping shape on it. False work is these things. On the Clyde Dam, we were employing qualified chippies to put these in, paying them a lot of money. So it's the pegs that go in the ground and the timber that goes to brace it. The bracing side of things is called the false work, right? And that's normally not reused either. They use double-headed nails on that with a nail gun, so that they can pull the nail out quickly to pull it apart to move on to the next bit. You normally leave that on there for a couple of days, that's about it. Like then they had a guy full-time employed to chop that up for firewood. It was given to the staff, which is pretty impressive for Germans. Probably charged the government for it. I don't know. I won't go that far, that's a wee bit too far. But when you work on a New Zealand site, your family are often given an almost free house. And the Germans used to have this, they always have a ranking. And so the best houses in Cromwell were beautiful brick tile, carpet, lovely fires, everything. And then maybe the draftsman would get the next one, and so on to the workers, who got pretty crappy houses. But the stupid Germans did a whole street of German houses, and then a whole street of normal staff houses, and a whole street of labouring houses. So on a Saturday night, the labourers used to get on the drink. They had too much to drink, and nothing else to do in Cromwell but drive down German Street, yelling out names and throwing all their beer bottles all over their sections and properties and driving off. So if they had scattered their houses amongst everyone, that wouldn't happen. But But because they did it that way, it was like, oh, where are we going on Saturday night? Oh, let's go to German Street. It's perfect, right? So they also, when you're on a big site like that, you get paid an extra allowance for being on a big building site. And Cromwell, being away from home and away from big cities and things, Cromwell was only 10 minutes drive from the site, and it was a proper city with supermarkets and all the rest, or proper town, I mean, yeah. So it wasn't that much of a hardship for everybody, but anyway, that's what they used the formwork for. There is a question on the difference between plain bars and deformed bars. Please read that section. And there's a question on the most common grade that we use in New Zealand for our reinforcing steel. Common grade is now grade 300. Driveways. I said before it was plain concrete. Most of you probably never helped your dad pour a bit of a driveway or a path. But these days people tend to put the mesh reinforcing in there as a token gesture to keep the concrete together for another 10 years. But it's not proper concrete design like we would do here, or like you do in Lucy's class, who's due very soon. I just feel it. I don't know what. There's a question on pouring of the concrete. So the hoist and the chute is where they kind of pump it long distance. So if the question in the test is that the house pour or the dam pour, the reinforcing pour is quite away from where you can park your concrete truck, what's the best method? A wheelbarrow, a bucket, pumping, or hoist and chute. The hoist and chute's got limitations, probably about 30-40 metres, but pumping can go quite a lot further. They have to, if you have that situation, you need to tell the concrete company, because they need to do a number of things to make sure that if you're pumping it through that much, you're going to have to watch your fines, how big your concrete is, so they'll do another redesign on it so it goes through the pump. The cover of the concrete's important. There's also a question on that in the test. The reason for the cover is things like salt water can affect the reinforcing bars, so you want more cover if it's a concrete wall by the ocean. Geothermal down Taupo Way, if you're going to build anything down there, if it's in a geothermal site, that can affect the reinforcing. Or just straight rain and air can also affect it. Also ground conditions, different types of soils can affect the reinforcing. So it's all about a geotechnical engineer. Yep, he comes into play again, or she, and they get to say on what the cover of the reinforcing should be. And sometimes it's different at the bottom to what it is on the sides. The lap is our way of extending the bar, so if we only have a certain bar length and we want to make it longer, then we lap it. And the lap is either calculated at 32 times the diameter of the bar, or a plain bar 40 times the diameter, or you look at that little chart that I showed you before, it'll be on there. Remember the one that had I said when you shorten the bar, and it told you how much to take off. There's also got a diameter on that as well. There's a very simple way of drawing up a reinforcing wall, but what the most important thing here is it gives you what each thing breaks down to on the caller. So 8 bars deformed, 16 is the diameter of the bar, 01 is the first mark, spacing, and each face would mean it's on both faces of the wall. We have abbreviations which come into play further down. We have each face, we have the near face and the far face, and we have both faces, which is each face. We have top and bottom, and sometimes the reinforcing is top, bottom, each face, and each face. So it can be a combination of things. The reason for that is that the steelie will put all the steel on site in one area for each face. So you'd start from the bottom, you want quick access to that steel to do the slab. And then the next piece up, that's over there, we'll use it, and the top stuff would be further away for doing anything up the top. So they stack it on site according to when you're going to use it. It's logical, I suppose. These typical allowances are also helpful, but once a sheeted chart's provided, like I've done, that overrides everything, right? I'm going to get students that aren't in this lecture today, they're going to be using some of these notes, and they'll be wrong because the chart has been provided. All the information is on there if you need it. Sometimes it'll be exactly the same, sometimes it'll be a little bit out. And here's a little example of reinforcing schedule. Alright, and that's actually a wee bit more like your one in your assignment. So it's probably worthwhile looking at that as well, how it's drawn and all the rest. Here's all the abbreviations and what they mean. I have grabbed a couple of these for the test. It's easy fodder. Probably a page you could have open in the test. You're bound to get one if there's 3 or 4 questions. You're bound to get one there. These things can be very handy when you're writing notes. A lot of students say to me, we only had that little space there to write our notes. I said, did you use abbreviations? No, we wrote it out in full. You know, things like precast, pre-stressed concrete takes up a lot more than PSC, for example. So that's kind of that. We will, in our lab, be going over an example, which will take me the best part of an hour. So please be there, okay? And please film it if you feel you would like to go back over that. And I think you'll all find that if the light bulb goes on, you'll find that the assignment's actually quite a bit easier than the example I'm going to be going over. Okay? There's a lot there, but at least I've handed you out the assignment first up, to give you a chance to analyse it early on in the